So I will write a second problem sheet that counts as the final exam very soon and put it on the site because some people need a mark. Third and fourth year students need a mark by the end of May. So I'll put it up soon. But for other people who don't need the mark right away, I'll probably set the date as maybe second week of June. Is that okay? You seem unhappy about that. The sooner we're all done, the better. I'm getting tired. Okay. Okay, so we have talked about regular local rings. We've given some examples. We want to give a characterization, but this will take some building up to. So first we need to talk about what's called depth. So there's depth of a local ring and depth of a module over a local ring. So we're talking about depth and projective dimension and the relation between them. So A is local Noetherian ring today. Everything is about local Noetherian rings. It has a maximal ideal called M and a residue field, which is A mod M, called K. And we'll typically consider finitely generated modules. And the depth, let me give definitions. So a regular sequence in A, I think we already mentioned these, but let me mention it again. Is a sequence of elements F1 through Fn in the maximal ideal such that Fi is a non-zero divisor on the quotient by the preceding elements. And maybe you started out with 0, kind of, so that F1 is also a non-zero divisor. So just to emphasize, F1 itself, a non-zero divisor on A. And the depth of A this is the supremum of the length of regular sequences. And we'll see in a second that it's actually a max. So there's a maximal length regular sequence. So let's see that. So remember, we had these list of standard facts in commutative algebra, among which were these theorems of curl about codimension. And in the local case, that implied something actually about dimension. So by Curl's principal ideal theorem, every time I take a quotient by a non-zero divisor, the dimension of my local ring drops by 1. So dimension of A mod F equals dimension of A minus 1. And so if I have a regular sequence, we get that dimension of A equals dimension of the ring modulo of the regular sequence plus n, and we know that the left-hand side is bounded, right? We know that this is in fact bounded by m mod m squared. So we also prove that using this kind of argument. So this is greater than or equal to n. So the length of a regular sequence is bounded by the dimension of A. And so, so there exists a regular sequence of maximal length, and it's at most the dimension of A. Maybe it's strictly less. So what do we get? We get that the depth of A, which is the length of the maximal length of a regular sequence, is less than or equal to dimension of A, which is less than or equal to this dimension of the Zariski cotangent space. And remember, we defined regular where this was an equality. And in fact, we're going to see all of these are inequality. Okay. Very good. So now we need two more standard facts in commutative algebra. Maybe we'll spend some of the time in the seminar proving these things, if I can remember how to do it. So these are the two easy to state facts that we're going to use. And they're not really hard to prove. They just take a list of definitions that would distract us right now. So needed facts. Oh, I need one more definition. So I can generalize this notion of depth to a module over A. So definition, given A. I mean, the definition makes sense, I guess, for non-finitely generated modules, but we will have nothing to prove in that case. So let's say a finitely generated A module M, depth of M is, okay, well, I should say what is a regular M sequence. So a regular M sequence is a sequence of elements of the maximal ideal such that, like this, Fi will be a non-zero divisor on the quotient of M by this bit. So such that Fi is a non-zero divisor on M modulo. So I take the first I minus 1, I multiply them on M, that generates a submodule, and I take the quotient by that. So note, let me define the definition, then depth of M is the supremum of lengths of regular M sequences. Okay. And our first task is to show not only is this finite, but actually any two maximal regular sequences will have the same length, and we'll have some homological way to measure that length. Okay, so this is our first thing we want to prove, but maybe I need some standard facts to do that. So that's the definition. Where are we? Yes, so standard facts. So basically two. So fact A, if every if depth of M equals 0, so every element of the maximal ideal acts as, kills something in M. So annihilate some element of the module, some non-zero element. Then there's some element which is annihilated by everything in the maximal ideal. So the annihilator of X equals the whole maximal ideal. That's the first fact. And the second fact well, let me conclude something from this. Okay, so accepting that fact, so then if I define a map, which is multiplication on X, the annihilator, that is the kernel of this map, is exactly M. Therefore, the quotient, A mod M, which is K, the residue field, gets realized as a submodule of M. Because the kernel of this is exactly M. Okay? So thus, Hom over A from the residue field as an A module to M is non-zero. Okay, so that's the conclusion we wanted out of that. And the second fact we want is if the depth of A and of M are both non-zero, so there's a non-zero divisor in the ring, and there's some element of the ring, some non-unit of the ring, which is a non-zero divisor on the module, then there's in fact an element which is a non-zero divisor on both. Okay. So I need to move there. Yes. So that's fact A. Fact B, if depth of A and depth of M are both non-zero, then there exists some element of the maximal ideal which is a non-zero divisor on both A and M. So both of these facts are not very hard to prove. Both facts are part of the theory of associated primes, which is part of the theory of primary decomposition, maybe. But it's kind of more elementary. Okay. So we'll come back to them in the seminar. And so we're going to take these facts as given. And then the first big theorem about depth is the following. So theorem So A, Noetherian local, M, a finitely generated module. Those are our basic assumptions for all of today. Then all regular M sequences have the same length. And that length, which is the depth, so depth is now the length of any maximal regular sequence. So maximal means you can't add on an additional element and still get a regular sequence. It's maximal in the sense of inclusion. So this equals all maximal regular sequences on M. And this depth is exactly the minimum I such that the X group, Xi, from the residue field into M is non-zero. So this special fact was the depth zero version of this. So that's where the induction starts. So suppose, depth is zero if and only if there are no regular sequences. No non-empty regular sequences. So every element of the maximal ideal annihilates something, acts as a zero divisor. So depth, so we'll do induction on depth. Yeah, let me just spell that out. So if depth is zero, then Hom, which is x0, is non-zero by fact A. Conversely, suppose this Hom is non-zero. I claimed that that has to be the depth. Suppose Hom A, K, M is non-zero. Then what? Then let X in M be the image of some non-zero map. So it'd be image of 1 under a non-zero map. This is a map of A modules. We know that there is such a thing because of the hypothesis. Then every f in the maximal ideal annihilates x, because A surjects onto K and kills everything in the maximal ideal, and then it acts on X. So no matter what f I pick, it will always annihilate some non-zero thing, and so the depth is 0. Okay. Now we want to consider higher depth. So in fact, we'll proceed now on induction on the length of a maximal regular sequence. Let's proceed by induction on length of maximal regular sequence. So let's suppose we've already done this for maximal, when there's a maximal regular sequence of length n minus 1. Let's take one of length n. So let f1 through fn be maximal regular M sequence. Then f2 through fn is a maximal regular sequence on the quotient. And since f1 acts as a non-zero divisor on M, we have a short exact sequence, which is act by f1. Being a non-zero divisor exactly means acting by f1 is an injection. And then I have the quotient, m mod f1. Now I'm going to hum in the module k and take the long exact sequence in x. Okay, so what does this look like? By induction, here, I have a maximal regular sequence of length n minus 1. I know that they all have the same length. And I know that that length is detected by the minimal non-zero X group. So that will occur at n minus 1. So we get, by induction, we get what? So in the low range, before n minus 1, everything here will be 0. And I'll just have isomorphisms here. Right. I'll get isomorphisms like this, which are given by multiplication by F1. And that happens in the range I less than or equal to n minus 2. But these things are K modules because I'm humming out of K. These are A mod M equals K modules. So F1 actually acts trivially because F1 is 0 in K. So if I have an isomorphism, but it's 0, then the modules are 0. Right, is that what I wanted? Actually, this observation works for all I. So let me first make this observation. So I have these maps for every I, but these are all these modules in this X by 0. So this map is always 0. Okay, and so then for I less than or equal to n minus 2, I get that xi km is 0. And what's left is what? So the first non-zero axt into m mod f1 by induction is this one. So I know that that's non-zero. And then I'll have an axt n into km. I'll have multiplication, which will be 0, and then it will continue. And I don't know what happens after that. Okay, so this is 0, therefore this is a surjection. And what? Here I have xn minus 1 into m, and 0, and also xn minus 1 into m. And then the previous term is 0 by induction. So this is supposed to be an injection, but it's 0. Therefore, this module is 0. Therefore, this module is 0. Therefore, this becomes an isomorphism. So this module is non-zero. Okay, so that's what we wanted by induction. And so that n is exactly this minimal non-zero axt. So homological algebra detects the length of a maximal regular sequence. Okay, so that's that first theorem. You can do something similar for injective dimension. I'll probably give an exercise about that in the final list of problems. So everything we did about projective dimension tends to have an injective dimension analog. And in certain applications, the injective version is more useful or natural. So I think I'll make a sequence of exercises about it. That's what I did last year. There you go. And so that was about detecting depth via non-vanishing of X. Now, we also were interested in projective dimension of a module. And we can detect this, or at least get a bound on this in terms of Tor. And then we'll use this bound to relate depth and projective dimension, and that will get us toward the characterization of regular local. Okay, so with A, again, local Noetherian. Probably M finitely generated. M finitely generated. Then the projective dimension of M is less than or equal to I if and only if Tor I plus 1 against the residue field is 0. So the projective dimension is the largest I for which this is non-zero. So projective dimension of M equals the supremum. It could be infinite. The supremum of I such that Tor I is non-zero. Okay. So let's give a proof. The proof that Weibel gives is maybe not ideal. For some reason I don't understand. He always avoids using minimal resolutions, but we have them. They're very natural, they're very useful. So let's choose a minimal resolution. So let F0 mapping to M, mapping to F1, and so on. Let this be a minimal resolution. Then whatever the length of this is the projective dimension. Maybe it's infinite. And we already know that the rank of the ith term can be computed in terms of Tor. So when we, in the seminar, talked about minimal resolutions, this is one of the things we showed. And that's just because a resolution was minimal if and only if when I tensored with k, the differential became 0. Sorry, this is dimension over k. Okay. So the only way this thing here, this module could be 0 is if its rank is 0. These are free modules. And that happens if and only if the module on the right is 0. Okay, so that's all there is to it. Very good. And then we have a corollary of this. So the corollary is that, so remember we had homological dimension of a ring. So that was the supremum of all of the projective dimensions of the modules. Maybe it's infinite, but maybe there's some universal bound. Sometimes there is. Then we also know that the same is supremum of projective dimensions for quotient rings of the ring. And so that's what we call the homological dimension. And the corollary says that for a local ring, there's a special module whose projective dimension is big as possible. So let A be Noetherian local. Then its homological dimension equals the projective dimension of the module A mod M of the residue field. So that's the biggest that the projective dimension can be. Both sides can be infinite. It will turn out that when they're finite, this will turn out to be exactly the case of regular local rings, but this will take more work. Okay, so proof. So the projective dimension of A mod M, of course, is less than or equal to the supremum of all projective dimensions of quotient rings, because it appears in there. And we showed that when we first introduced projective dimension, we showed that was the homological dimension of A. Yeah, so maybe I should have written it like that. So this is the homological dimension of A. So I get one inequality. And now this guy I claim by what we just did here is less than the so-called flat dimension of A mod M. Why? So I could bound the projective dimension of A mod I by vanishing of Tor. And I can compute Tor in one of two ways. I can either resolve M or I can resolve K. But M is varying K is fixed, so let's resolve K. Let's take a minimal flat resolution of A mod M. So that will give the flat dimension. Then whatever that is, Tor beyond that must vanish, so that bounds the projective dimension. So this is where we use the proposition. So use proposition and flat resolution of A mod M. And projective resolutions or free resolutions are in particular flat. So maybe some flat resolution is shorter a priori than a projective one. But any projective resolution will give a flat resolution. Okay, so this is because projective implies flat. Okay, and so now homological dimension of A is in between these two projective dimensions of A mod M. So that's what we wanted. So this is some special module that has maximal homological complexity, longest possible projective resolution. And that's why that's the module that we either hom out of or tensor with to detect things about the homological information of other modules. Okay, very good. And now another corollary of this similar flavor. And then we'll change gears a little bit. So second corollary. A is again Noetherian local. And homological dimension equals projective dimension. Then, I think that's the one I just did, sorry. So A is Noetherian local, and F and M a non-zero divisor. So let's suppose we have such a thing. Then, so in particular, the depth is positive. So then, either the homological dimension of the quotient ring, A mod F, is infinite, or the homological dimension of the original ring is that of the quotient ring plus 1. So this is good because it allows us to do induction arguments on homological dimension. And we've already seen lots of things like this, these change of rings theorems. So we're going to be using change of rings theorems in the proof. So the proof is the following. Suppose maybe not, thank you. Maybe not. Oh, you know what? I don't need to because I didn't move it on the previous step. Problem solved. Yeah, this is not a great situation.
You can show what you need now.
Yeah, let me go back a bit. So let people stare at this for a minute. So the proposition was Noetherian local ring M finitely generated. Then we could, if we want to bound the projective dimension of a module, we need the next Tor group to be 0. And so in particular, the projective dimension is the biggest non-zero Tor group against the residue field. And then the corollary of this was that homological dimension of the ring was the projective dimension of the residue field. And we got that by a sequence of inequalities. Okay. So these proofs are in Weibel. The difference between what Weibel writes and what I present is that it's easier to use minimal resolutions. The proofs are much shorter sometimes if you use minimal resolution. So in this proposition, we chose a minimal resolution of M. And Weibel, for some inexplicable reason, avoids doing that. Okay, so the second corollary. So the second corollary is the following. So I have an Noetherian local ring. Then either the quotient with a non-zero divisor, then either the quotient ring has infinite homological dimension, or the homological dimension of A is that of the quotient ring plus 1. So if it's infinite homological dimension, it is, and there's nothing to prove. Otherwise, let's assume it's finite. Suppose homological dimension of A mod F is finite. And we know by the previous corollary, maybe we'll use this, that this is the projective dimension over A mod F of K. And now we have the first change of rings theorem. We know that it exactly tells us how projective dimension of K over A compares to projective dimension of K over A mod F. So projective dimension of K over A is projective dimension over A mod F plus 1. Which is what? Well, that's homological dimension of A mod F plus 1 by the previous corollary, and this is homological dimension of A. Okay, so that's the second corollary. Okay, so that's what we can say about the special residue field. And now we want to get more into depth and the relation of depth to projective dimension. So we're aiming at something called the Auslander-Buchsbaum formula. Okay. Yes, please. We showed that I defined it in terms of projective dimension, but there's a comparison. So there was I don't remember if did we have this theorem that the injective dimension and projective dimension were the same? They were both, could be measured in terms of non-vanishing of x. And you can compute x either by resolving the source with projectives or the target with injectives. And so it doesn't really matter. But I thought that I defined it in terms of projective dimension. Okay. Okay, well anyway, there should also be a statement that these are the same, and you should be able to see this from the characterization in terms of x vanishing. Okay, so now we have what's called the depth zero lemma. So this will get an induction started. Sometimes people call depth grade. Right. So suppose that the ring has depth 0. So every element of the maximal ideal is a 0 divisor. So a simple example would be A is a field, and the maximal ideal is 0. And so obviously it has depth 0. Then for any finitely generated module, there are two possibilities. Either the projective dimension is 0 or the projective dimension is infinite. There's nothing in between. So of course, the first case always happens if A is a field, but there could be some more complicated ring. So for example, let me get a ring where you can see both things happening. So suppose A is the ring polynomials in T over a field modulo T squared. That's a local ring. M is the ideal generated by T. Okay. It obviously has depth 0 because T annihilates itself. So it's not a 0 divisor. And everything else in here is just a multiple of T, a scalar multiple. Okay, so this has depth 0. However, you can check, and it's probably implicit in other exercises that we've done, but maybe let's do this in the seminar. You can check that the homological dimension of A, which always is the projective dimension of the residue field, which in this case is just the K you started with. You could check that that's infinite. So basically, you can write down a minimal resolution of K and see that it goes on for forever. So it has a very simple but infinite minimal resolution. So minimal resolution of K is infinite. And then the claim is that the only other possibility, so what does projective dimension 0 mean? It means projective, but we're over a local ring, and it's finitely generated, so that means free. So the claim here is then any module of finite projective dimension is already free. So we'll see this in general, but we can analyze this example more in the seminar. Something similar will work if I took kt mod t to the n. There's nothing special about t squared. It would still be depth 0. And remember, depth is bounded by dimension, by curl dimension. Curl dimension of such a ring is 0. If polynomials are functions on an affine line, these are functions which vanish to some order at the origin. And the origin is 0 dimensional. So this is what's going on. So it's a kind of fuzzy, thick point supported at the origin in the affine line. Its functions there. Okay. Right, so the proof. If the projective dimension of the module is infinite, it's infinite, there's nothing to prove, so let's assume it's finite. So suppose projective dimension of M is finite. Let's suppose it's called D, and that's finite. So then, whatever the minimal resolution is, has length T. So consider the minimal resolution. Actually, yeah. So each of these is a free module of some finite rank. And the last one embeds into the second to last one. Okay. So these are free of finite rank. And now I want to consider what happens at this end. I'm expecting, according to the lemma, that in fact, there's no resolution. It has length 0. That this is an isomorphism, and then there's nothing out here. And so I'm going to work from left to right and show that each of these terms is 0. Okay, so in fact, I don't even have to consider it a Milnor resolution. Just consider a finite free resolution. And then I'll show that I can eliminate terms and go all the way down to 0. So consider finite free resolution. Okay, so now consider this, and then there's a co-kernel. Right? So I have a free module and a sub-free module, and the quotient is what it is. Maybe I do want minimal. Just a minute. Yeah, maybe I did want minimal. Okay, so I have this, and now tensor with the residue field. Then by minimality, the number of free generators here is the number of generators there. Remember how we construct the minimal resolution. We had the kernel of, the previous differential, and then we chose a minimal set of generators that mapped onto it. And so if I apply this, then by minimality, and the Nakayama lemma, I get that fd minus 1 tensor k is isomorphic like this. So I get the following. I have f d minus 1 I'm going to write f bar for this. This is an isomorphism to c bar. This is c. This is fd. I have fd bar, like this. And this, whatever this is 0. Right? Because this is an isomorphism. And then there's some Tor term that I don't care about. And now what are the kernel of these vertical maps? I'm reducing mod m when I tensor with k. So the kernel here is maximal ideal times fd minus 1. And so this composite is 0. Therefore, fd lives inside here. So FD is a submodule in maximal ideal times FD minus 1. Because this differential is 0, because this is an isomorphism. This was Nakayama. And this is from the Longuezec sequence of Tor. But what is our hypothesis on the ring? We suppose the ring has depth 0. That means every element of the maximal ideal is a 0 divisor. So choose by fact B. Was it fact B or fact A? I erased them. So choose by basic facts. And probably an X in C no in X and M. Just a minute. Yeah. So A, the ring, is depth 0. That means everything is a 0 divisor, and I can choose an X which is annihilated by all of M. So that was part of the facts. So this is F such that Fx equals 0. So remember, the list of facts said if every element of the maximal ideal was a 0 divisor on the module, then there was some module element whose annihilator was the maximal ideal. Okay, so that's what it says in this case. So since depth of A is 0. And now, screen. So since this module FD is contained in the maximal ideal times FD minus 1, then X, this element that I chose, annihilates D. So this is inside X times M times FD minus 1, and M annihilates X, so this is 0. Okay, so the single element X annihilates all of D. But then, therefore, M annihilates all of D. Actually, I should have said this. On the other hand, FD is free. It was part of a free projective resolution. Okay. So it can't be annihilated by a non-zero element unless it's 0. And so now the resolution I started with can be shortened. Now it has length d minus 1, and I can repeat. So repeating the argument, we'll find that fd minus 1 is 0, and so on. Okay. So in the end, the minimal free resolution that we started with, in fact, had length 0. Okay, so that's the depth 0 lemma, and this will be the inductive step for the Auslander-Buchsbaum formula. So I think we have 10 minutes? Okay, I hope this is enough. Okay. So theorem. So in case I forget at the end, I wanted to make an announcement, which is that I heard that PhysTech is opening up a pure mathematics program with positions for master students. So most of you are already master students, so it's not relevant to you. But to anyone out there who's interested in looking for a place to be a master student, this is a possibility. Okay, so let A be a Noetherian local, as usual. M finitely generated module. So if the projective dimension is finite, then we have the following formula. So among all modules, some of them have projective dimension, maybe not all of them. But if it does, then the depth of A, which is definitely a finite number, equals the depth of the module plus the projective dimension of the module. So there's complementary relation between depth and projective dimension for a module. So let's consider a few cases. It'll be a kind of double induction where we have to induct on both depth of A and depth of M. So first step would be if depth of M equals 0. If depth of the ring equals 0, and projective dimension of the module is finite, then the depth 0 lemma says that the projective dimension of M is 0. But if the projective dimension is 0, that means it's actually itself a projective module and therefore a free module because we're over a local ring. So, but then M is finitely generated and free. So the depth is the same as that of A. Which was 0. So every element of the maximal ideal has to be killing something in a finitely generated free module. For instance, take something that it kills in A and just make the kind of diagonal tuple out of that in your free module. Everything acts as a zero divisor. Next case, suppose that the depth of the ring is non-zero. But the depth of the module is 0. And then it will remain to do the case where they're both non-zero. Choose the depth of A is non-zero, so choose F in M, a non-zero divisor. There's at least one non-zero divisor because the depth is positive. And a non-zero element which is annihilated by the maximal ideal. So the depth is 0, and so everything acts as a zero divisor, and by these facts, there exists such an X. So the annihilator of X equals M. So this was from the facts, that there exists such an X. And now let's try to resolve M. So the beginning of a resolution of M, it will be surjected onto by some number of copies of the ring. It's finitely generated. And then there's some kernel. And under this surjection, I can choose a lift of this special element X. So I have here X, and I have some lift of it, any lift of it, call it X tilde. So if I take this X tilde and I multiply it with anything in the maximal ideal, notice that I end up inside of the kernel. Because when I multiply the maximal ideal on X, it becomes 0. And so in particular, because the non-zero divisor F that I started with was in the maximal ideal, I have that F times this special module element, X tilde, is an element of the kernel. Right. So, but then, if I multiply the whole maximal ideal on this element F dot X tilde, all of that has to live in F times K. Just rearrange, pull the element F out here. Right. On the other hand, F times X tilde itself is not an F times K. because if it were, we'd have f times x tilde equals some f times y with y and k. And then f times x tilde minus y would be 0. But this x tilde minus y, it lives inside this free module. And f was a non-zero divisor on A. But f is a non-zero divisor on A to the n. And x tilde is not in K because it mapped to something non-zero in M. So x tilde is not equal to y. Okay, so this would be a contradiction. So f times x tilde is not in f times K. And this argument works for any non-zero divisor in A. Okay, so what does that tell us about K? Or actually about K mod F? So then let's consider K mod Fk. Where is it? I want to claim that implies it has depth 0. I see, because of the maximal ideal. Yes. Very good. So then depth of this quotient module I claim is 0. Because why? So if it was not 0, then there would have to be some element of the ring which acted as a non-zero divisor. On the other hand, we know that if I multiply the maximal ideal on this special element, then it always lands in here. So anything that I want to be a non-zero divisor will actually fail to be a non-zero divisor to land me in this kernel of the quotient. So this is because M because any element of M annihilates this special element, the special non-zero element in K mod Fk. So now K mod Fk has depth 0. And this is going to allow us to control something about K itself. Need to move the screen again. Okay, so we're about out of time. Let me end this case and we'll do the next case next time. We'll finish it off and then we'll do the characterization, homological characterization of regular local rings. Okay, so that means depth of k mod f, k is 0. And k is a submodule of a free module. So what does that mean? So f is a non-zero divisor on k. And then by the third ray change of rings theorem. So remember, the change of rings theorem were typically about you had some element of the ring which acted as a non-zero divisor. Right. We have the following. So we have projective dimension of A over A mod F of K mod F. This is projective dimension of K. Which, where is it? Because of this sequence, the projective dimension of this is one less than the projective dimension of this. This is projective dimension of M minus 1. Okay? And then the depth of A mod F is also one less than the depth of A, because we modded out by a non-zero divisor, and so we've shortened the length of a maximal regular sequence. And so we get altogether the depth we're trying to understand, depth A, this equals 1 plus the depth of the quotient ring. By what we just said here, this is probably by induction, right? So here this is by induction. The depth of A mod F will be depth of K mod F, K, plus projective dimension of K mod F, K. And then here, from this formula, we can put in projective dimension of M minus 1. So this will be depth where is it? Projective dimension here will be, right, projective will be depth of K mod Fk plus projective dimension of AM. Okay, and what I wanted was depth M. So why is this the same as depth K? That term's 0. That's fine. Sorry. Better way to say it is that I know that that term's 0. So this was by induction. I can write this equals this. But I know that term is 0. And then projective dimension of this module plus this module is here. So the 1 and the -1 cancel, and I'm left with the projective dimension here. But I seem to have lost, did I lose a term? No, that's perfect, because what is the hypothesis? It was this, that the depth of M is 0. So this term here would be depth of M, but it's 0. Okay, and so one case remains. Next time, we need to do depth of A is not 0 and depth of M is not 0. Okay. So we'll do that next time. We'll stop now.